This is section 6.7, rotation symmetric. Okay, so what we're going to be talking about is some more stuff with symmetry, but instead of symmetry where we can take a shape and fold it over and get the same thing, what we're going to do is we are going to take shapes and turn them and get the same thing. So they kind of give some pictures of things that are rotation symmetric in your book there. So they've got a playing card, they've got like a wheel of like a ship, and then they've got like a windmill there. All of those things would be rotation symmetric because we could take them and turn them and they would look the same when we turn them. So like that first thing there, that playing card, I've got a playing card here. So if I took this playing card here and I turned it all the way upside down, it looks exactly the same. Now you'll just have to ignore that hole there, that's because it's from a casino. But besides that hole, if you took and turned that card, it looks the same on the top and the bottom. The reason they do that is because if you're holding it in your hand like this, playing cards, you can either hold it this way or you can hold it this way and it looks exactly the same. So it's just more convenient for the user if you can use it both ways. So right side up and upside down are exactly the same. So that's one thing. Another real life thing that you see a lot of symmetry in would be like bits. So you've got your regular bits like a Phillips bit here, where you would go into like a screw like this. Screws would be rotation symmetric because this Phillips here, when you take and you turn it, you're going to turn it 90 degrees and get the same exact shape there. A lot of these, or all of these bits here, whether it's a square bit, or the Phillips, or the flats, or the star bits, all of those are rotation symmetric because you're taking and turning something and you want it to be the same all the way around. Otherwise, when you turn it, it's not going to be very convenient to use your tools. But like a lot of things like nuts and bolts, again, we've used this as an example before, but if you take and you turn it, you want it to be the same on all those sides so it's easy to hook your wrench on. Okay, so a lot of rotation symmetry type things in real life. Okay, so first thing there, definition of rotation symmetry on 351. So it says a plane figure F is a rotation symmetric figure if and only if there is a rotation R with magnitude between 0 and 360 such that rotation of F goes back onto F, and the center of R, or the center of rotation, is the center of symmetry for F. Okay, so what they're saying there is if I took my shape, whatever it was, I'm going to turn it so far and it's going to go back to the same shape. Okay, so like right now I've got the flat part up, so if I take and turn it so far, I again have the flat part up. I got another thing here, so this is just a shape I kind of cut out. So like, say it was up like this, I'm going to turn it a certain amount of degrees. So now my green part's down here, but that shape looks exactly the same with the flat there, flat there, flat there. Again, I could turn it again, so I have flat on the top again, and this little wedge, you can see that it's turning around there, but it's still staying the shape, with the flats there and there and there. You're just turning it, but it's still staying the same. So when they talk about the center, your center of rotation is basically the spot that you're turning around. Like if I took like a stick or something and held it down there and then went and twisted it, that's what I'm spinning around. Or if you think about like on a pinwheel, how it's got like that little circle in the middle of a pinwheel, that would be the center of your rotation of the pinwheel because that's what you're spinning around. Okay, what do we have next here? So when it says n-fold symmetry, n-fold rotation symmetry, when the smallest magnitude of a rotation that will map onto itself is m, where m is 360 divided by n. Okay, so when they talk about folds, if I go back to this here, this would be a 1, 2, 3, 4, 5, 6, 7, 8. This would be 8-fold symmetric because each one of these little wedges, so it kind of looks like a little kite here, each one of those is going to be exactly the same size. So this would be 8-fold because I'm splitting it up into 8 equal chunks, where if I take and turn it a certain amount of degrees, I get back to the same shape. So to figure out the amount of degrees that you need to turn it to get back to your original shape, what you do is you take 360 and divide it by your number of folds. So like in this one here, I had 8 different folds, so 8 different sections I could have colored in green there that are all the same. So what I would do is I would take 360 and divide it by 8, and that would tell me how many degrees I have to take to turn it to get it back to the original shape. Okay. Another example that you might see in real life, this is supposed to represent like a kids type block. So you know those games that little kids have that they try to match like the shapes with the, so usually like a container with holes in it that they try to, you know, put the shape into the container. So this is kind of an example of this. What this is kind of representing here is there would be 5 different ways for this shape to fit up with these parts here, okay, because each one of these are all the same distance away, so there would be 5 different options that you could turn it and still fit into that gap there, okay, so that's just another real life example. And this would be considered, so when they're talking about end fold, this with the 5 sides here, this would be considered 5-fold. Because what you could do is if there was like a center there, you could break that up into 5 equal triangles and turn there 5 times to get back to your original shape. What else here? So if we're gonna try this, we usually don't do these, but it's like QY2. They're just like little questions. So it is on page 352. Basically what they've got is they've got 4 different pictures there. I'll put them up here. You've got 4 different pictures here, and you are trying to find 2 things. You are supposed to find the number of folds and the amount of degrees it's going to take to get to move that to back where the shape's the same. Okay, so like for this first one here, let me get my paper up here. For this first one here, for A, what we've got is we've got like 3 things sticking out here, so I would call this 3 folds. So my N, or my number of folds, would be 3, and then to figure out how many degrees I need to take and turn this so it's in this position here, I would take 360 and I would divide it by 3. So if I do 360 divided by 3, I get 120, so that would be what my M is. Okay, so you do that with the next shape as well. So like for B, I'm going to get it into my area here. For B, we're going to do this. Do it right here. Okay, so B, this is going to be 2-fold. So if I took the Z, it's kind of like the playing card. Playing cards are 2-fold. If I took and turned it completely upside down, it would be exactly the same. Same works for the Z. If I take and turn it up exactly upside down, that would be the same Z-looking shape. So my N here for my number of folds is 2. And then to find my degree amount, I would take 360 and divide it by 2, which is 180. Okay. Next one there, C. What I would do is I would count up how many little spikes are out here. So like the longer spikes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. So my N is going to be 10. Then to find my M, I would do 360 divided by 2. Oh, not 2. 10, which is my N value. And that would be 36. So 36 is what my M would be for that one. And then the last one with the square for D, this is going to be 4-fold. So my N is 4, or 4-fold. And then you would do 360 divided by 4, which would be 90. Okay? Alright. Book out of here. Alright. Next thing. Rotating is the same thing as reflecting over 2 lines. And those 2 lines you might want to put here have to be intersecting lines. So you remember, I don't know, it's been two chapters ago probably when we did reflections and we did them over multiple lines. When we had crossing lines like that and we did reflection over one and then reflection over the other, it ended up looking like a rotation or a turn. Okay, so that's kind of what they're talking about with this, and that's going to kind of lead us into our example here. So on your example sheet, we're going to do this one down here. So it says rectangle RECT has 2 symmetry lines. So we got one here, P and Q, that intersect at point O, so crossing in the middle there at O. And we're supposed to explain why this has rotational symmetry. Okay, so it says because P and Q are symmetry lines, if we take and flip this shape here over P, so basically we're flipping over this line here, so if I take R and flip it over, I'm at E. If I take my next one there, E, and flip it over, I'm at R. And then if I take, what's my next one, C, and flip it over, I'm at T. And the last one, T flipped over, is C. So that's just doing a reflection over P. And then if I take and do a reflection over Q, so I take my original shape here, and I flip it over Q, so R flipped over Q would be T. E flipped over Q going this way is C. What's next there? C flipped over is E. And T flipped over is R. So they say, and then by substitution, so basically just combining those two flips together, then we would get, so with this one we have to take, you remember from a couple chapters ago, whatever's furthest to the right, we flip over first. So that was when we flipped over Q, so I'm just going to use these letters here and then flip those over P. So if I take these letters here, T, and flip it over my vertical line here, so T flipped over, that would be C. What's my next one? C flipped over is T. E flipped over is R. And then the last one, R flipped over is E. So then it says lines P and Q intersect, so that we know if we do a reflection over P following a reflection over Q, it is what? Well, that would be a rotation, since we are flipping over two lines that are intersecting each other by reflection theorem of rotations, which is a theorem we've had before. And then it says this rotation maps the original rectangle onto itself in a non-trivial way, so it's just saying it's rotational symmetric. So it's just saying because we've got those symmetry lines there and they cross in the middle, we can rotate it and get it back onto itself because we're flipping over those two lines that are crossing there. Okay, next thing, this always is funny to me. The name of this next theorem is just theorem. I don't know why it doesn't have more of a name, why they didn't give it more than theorem, but it is just called theorem. So it says, if a figure possesses two lines of symmetry intersecting at one point P, then it is rotation symmetric with the center of symmetry at P. So that's kind of just like saying what they had on this last one here. If you've got two lines here of symmetry and they meet up somewhere in the middle of your shape, you can rotate around that point there where they meet and it'll be rotation symmetric. Again, I don't know why it's called just theorem, but it is. And then the last thing we've got here is just a list of quadrilaterals or four-sided figures with rotation symmetries. So rectangle, square, parallelograms. Also rhombus fits in this category. So rhombus is also rotation symmetric. Ones that people kind of get confused on sometimes that are not ones, so these are ones that are not rotation symmetric, are kite and trapezoid. So those are reflection symmetric, but if we go and turn those, you don't get the same shape. So just be careful on those ones. Okay, so that is it for notes. So your book page assignment is 353, 1 to 15, and you can cross out number 12.